I thought I'd give you a brief case study of some condition assessment in a particular domain. And I've chosen this domain, which is the domain of sewers, not because I love sewers, but because I've done a lot of work building robots to go through sewers and looking at the different ways that they can actually fail and working out what condition that they're in. First, though, let's look at the domain of sewers. And basically, we've got millions of kilometers of sewers in the world. And one thing that they have in common is they connect up to our houses. So we have these huge networks of pipes which are somehow connected to most of our houses, unless we're on a septic system where we take care of it ourselves. Quite commonly, these are gravity fed. And so the flow of the sewage, the effluents, and all the water and things is flowing down until it's pumped up to a different location and then flowing down and it's pumped up. And we have this gravity feed often going. There are pressure fed sewers as well, until it gets to a water treatment plant typically. That's how these things work. And we have a whole bunch of different types of sewer materials. These things can be made of clay, VC is what it's commonly called. They can be made of concrete, for example. And commonly these days we construct our sewers from PVC, a type of plastic, polyvinyl chloride. So we've got different types of materials, different types of pipes. We've got different sizes of pipes. Now, typically the pipes that go to our houses might be quite small. They might be 90 or 100 mil or something like that. But as a bunch of houses flow into a pipe, that pipe size will need to be larger. So it might be a 200 mil pipe or a 300 mil pipe when we've got a whole lot of houses flowing into it. And then as a whole lot of those pipes flow into bigger ones, we might have 600 mil pipes or 1 meter pipes. And then as those ones flow into larger ones, we might have pipes that are large enough that we could drive a car down them and perform condition assessment with some sort of a huge car-based robot or a truck-based robot. That's when they're a few meters in diameter. So we're moving from something quite small to something quite large. And obviously we need to perform different tests on different types of sewers and different sizes of sewers as well. The other thing is we've got different soil types that these sewers are embedded in. Typically the pipes aren't just sitting in midair, they're buried underground. And so we've got different soil types, from clays to things that have a whole lot more movement in them. And we need to consider those things as well. I said they're underground. They're typically 1 meter underground to 100 meters underground for some much deeper ones. And so some of those are going to be a whole lot easier to access than others. And clearly we don't want to just dig these up all the time and say, oh, yep, that one's fine, just backfill it all. They might be under people's houses. They might be under roads. They might be under parks. But having said that, there's a lot that can go wrong with sewers. From things like fatbergs or baby wipe blockages. And just a public service reminder, don't tip cooking fat down the sink, because that cooking fat, though it's liquid at the time, it goes into the sewer systems, it cools down, it coagulates and forms what are called fatbergs, which are big lumps of fat that are tangled around tree roots and tangled around things like baby wipes, what they sometimes term as flushable wipes. The water industry basically says no wipes are flushable. The only thing that you should be flushing down your sewer is things that come from your body, as in, well, we won't discuss that, and toilet paper. Nothing else should go down your sewers. Another big problem is tree roots growing through sewers. And you see a picture here of what can happen when those tree roots get into the sewers. They can completely block up the sewers and nothing can get through. You can get cracking that's occurring depending on what materials these things are made out of. Deformation, where our round sewers, our circular sewers, can become oval sewers as they start getting crushed down. And so we're wanting to measure the ovality of the sewers in that respect. Sewers can collapse. And so this is kind of our worst case scenario, where we've got a whole lot of the sewer that's just fallen in and there's no sewer anymore. When we've got this happening under roads, we can get sinkholes opening up and cars falling into these things if they're big enough. We've got H2S degradation, where we've got hydrogen sulfide that degrades these sewers, particularly the concrete ones, and makes them not nearly as strong as they were previously. We have water infiltration issues, and you might say, oh, why is that an issue? Sewer pipes are meant to carry water along with lots of other unsavory stuff. But if we have big water events like a whole lot of downpour of rain, and a lot of that rain makes its way into the sewer system by finding cracks that are occurring or finding joins between sewer pipes, or even through the maintenance holes. There's a whole lot more water that has to go into, needs to be pumped along when we're doing our gravity fed systems from sewer pump station to sewer pump station, and also going into the treatment plant. And this can cause our sewer systems to overflow, and we can start getting raw sewage coming back into the environment out of manholes or things like that, or through areas where the sewer's been affected. So we want to be able to measure that and work out, oh, what's going on there. We might have vermin or pests infiltrating these sewers. And I've seen pictures of a goat in a sewer. I have no idea how a goat got into a sewer. It was a reasonably, maybe it was a 400 or a 500 mil sewer. And there was a goat walking around. I've seen videos of frogs jumping around in sewers and things as well. And we've also got potentially displaced joints where these sewers are meant to be joined. They're typically in lengths of maybe 2.4 meters or something like that. And if they become disjointed, and they might go like this, or they might go like this, we've got all sorts of strange things that can occur. And so then we can ask the question, well, how do we test? One way we can test is with our CCTV, and this is the oldest sort of technique and probably the most commonly used as well. These days we can use things like AI to automatically identify where those cracks are, or identify things that aren't quite right. We can use laser profiling, where basically we make the sewer nice and dark and we shine a laser line around the sewer, and that helps us measure our ovality of the sewer. Is it circular or is it becoming an oval? And we can kind of determine whether we've got discontinuities or missing material that's collapsed into the sewer using this technique. We can use ground penetrating radar and working out what's happening underneath the surface of our sewer. We can use ultrasound, once again, like ground penetrating radar. We're working out where the rebar is, what the condition of the rebar is. Are there any voids behind the sewer, for example? Sometimes they pump smoke into sewers and look at where that smoke comes out. If it comes out of the ground, there might be a hole or something like that where it's filtering through. We might be able to see whether people are connecting up their storm water systems to sewers, which is against the specifications. And we can also do penetrometer testing, where we can test some of those issues that are occurring with H2S and work out whether the outer wall of the sewer is solid or it's become gypsum and very soft, and we can actually penetrate that through. And so there's one of the robots we've designed to actually penetrate through with a load cell on there and work out how much force it takes to penetrate the outer wall of that sewer. And typically, if it's in poor condition, not very much. Well, 150, 100 newtons or so will go straight through the outer layer of it. If it's in good condition, it won't penetrate at all.